In this video, we're going to quickly introduce the idea of capacitance. Then we'll derive the capacitance of a parallel plate capacitor in terms of the area and separation distance between the plates. And finally, we apply our new formula for capacitance to a simple example. So in general, a capacitor is a pair of conductors where the charge on the two conductors is equal in magnitude but opposite in sign. And in our diagram here, we see that we can achieve this so-called equal and opposite charge by hooking the conductors up to a battery, which then pumps charge from one conductor to the other, resulting in equal charge magnitudes but opposite signs. So while a capacitor in general could be any pair of conductors, a parallel plate capacitor is a pair of conductive sheets where the separation distance is very small compared to the dimensions of the sheets themselves. And for now, we're going to assume there is nothing between the sheets. In other words, it's a vacuum in there. This result will eventually need to be generalized for the presence of a dielectric sheet, in other words, an insulator between the plates, because in practice, it's really hard to hold two conductive sheets separate at a small distance without using some kind of insulating film in between them. So we hook this thing up to a battery with voltage V, and we end up with a charge of plus Q on one plate and minus Q on the other. And capacitance tells you how good this thing is at storing charge. So the definition of capacitance is Q over V. That's charge per volt. This means that if the capacitor is twice as large, you get twice the charge stored on it for the same battery. And the units of capacitance are coulombs per volt, which is also called a farad. And we use a capital F for that. And so the main point of this video is to find the capacitance of this pair of large sheet conductors, which means we need to find out how the potential difference V relates to the charge on the plates Q, and then we can just take Q divided by V to get the capacitance. But to find the potential difference between the plates, we need to know the electric field between the plates. So to get at the electric field, we're going to start with an isolated sheet of charge. And as long as we're close to this sheet and stay away from the edges, the electric field is well approximated by the infinite sheet approximation. And I'll post a link to the video where this result was derived using Gauss's law. For a positively charged sheet, the result is that the electric field is a constant pointing perpendicularly away from the sheet, and it has a magnitude of sigma over 2 epsilon 0, where sigma is the area charge density on the sheet, and epsilon 0 is the permittivity of free space. Now, if the charge density is negative, the field simply points toward the sheet instead of away from it. And we'll call that charge density negative sigma, using sigma to indicate the magnitude of the charge. Note that the magnitude of the electric field is the same as it was before, and we're calling that sigma over 2 epsilon 0. So what happens when we place two large sheets at a fixed separation distance that's small compared to the dimensions of the sheets? The electric field contributions from the sheets are simply going to add vectorially in every region. That's the superposition principle for electric fields. So we get three distinct regions to investigate. Above the positive plate, that's region 1. Between the plates, region 2. And below the negative plate, we'll call that region 3. Now we draw the field contributions from each plate in those regions. And I'm color coding these. So first we'll do the field contributions due to the positive plate. So in each region, the field due to the positive plate points away from the positive plate, and it has a constant magnitude. It doesn't drop off with distance. So that field is pointing up in region 1, down in regions 2 and 3. Now we draw the field contributions from the negative plate. Again, the magnitude of that is the same in all three regions, and in every case, it points at the negative sheet. So we notice that the field contributions exactly cancel when we're outside the plates. In other words, in regions 1 and 3, the electric field is 0. Between the plates, the field contributions exactly add to each other. So between the plates, we end up with an electric field magnitude of sigma over epsilon 0. So there's the field between the plates of a capacitor. It's a constant, and the strength is sigma over epsilon 0, where sigma is the area charge density on the plates, and epsilon 0 is the permittivity of free space. So now that we have the field between the plates, we can compute the potential difference between the plates, and that will quickly give us the capacitance when we take Q, the charge, divided by V, the potential difference. To get the potential difference here, the fundamental approach is to pick a path for the electric field path integral. And that path is going to be A to B, where the direction of motion is aligned with the electric field for simplicity. So we're going to traverse this path, starting at A and moving our way straight down to B. At all times, the direction of that path is parallel to the electric field, and this makes the path integral much simpler. Note that the potential at point A, we called that V, and we made the potential 0 on the bottom plate at point B. That's our reference point for the potential. So the potential at point A minus the potential at point B, in other words, V minus 0, or just V, is given by the path integral of E dotted into dl as we go from A to B. And I'll post a link real quick to the introduction video on electric potential where this formula for computing potential differences was first derived. So now we just have to compute this path integral E dotted into dl. And with E in the same direction as dl for every path length increment, the dot product is trivial here. The dot product is just the product of the magnitudes of E and dl because they point in the same direction. So the dot product in the integral is gone. And with the magnitude of E being constant between the plates, we can pull that out of the integral. And so we get E times the integral from A to B of dl. But that path integral from A to B of dl, that's just the distance between the plates. So replacing the electric field with sigma over epsilon 0 and replacing that path integral with d, we arrive at a result of sigma d over epsilon 0. Next, we replace the charge density, sigma, with the charge divided by the area. So we replace sigma with q over a, and we end up with a result for the path integral of qd over epsilon 0 a. So there it is. The potential difference between these two plates is q times d over epsilon 0 a. Finally, we can compute the capacitance by taking the charge, q, and dividing by the potential difference, v. And that's just the basic definition of capacitance as charge per volt. So we take q and we multiply by the reciprocal of v, and we arrive at this expression q epsilon 0 a over qd. The q's are going to cancel there, and it turns out our capacitance is epsilon 0 a over d. And this is our standard formula for the capacitance of a parallel plate capacitor with no dielectric present between the plates. Finally, we're going to wrap things up with a simple example. So in our example, we're told that we have a capacitor constructed from two square plates, 10 centimeters on a side. These plates are separated by a gap of 2 millimeters, and we can assume the space in between them is evacuated, so we're not worried about a dielectric present between the plates. And what we're asked for here is the charge on the plates when they're connected to a 6-volt lantern battery. We're reminded that the permittivity of free space is about 8.85 times 10 to the negative 12 farads per meter. So the starting point here is to get the capacitance of this parallel plate capacitor, and then we'll be able to find the charge. So our capacitance is epsilon 0 a over d, and epsilon 0 is about 8.85 times 10 to the negative 12 farads per meter. The area of each plate is just the side length squared, and we're going to put this in SI units, so we have 0.1 meters all squared. The distance between the plates is 2 millimeters, which we'll write as 0.002 meters. And when we run the numbers on this, we get 4.425 times 10 to the negative 11 farads. Next, we're going to find the charge on the plates by just turning around the basic definition of capacitance. Capacitance is Q over V, and that means the charge stored by a capacitor is Q equals CV. So we take the capacitance from the first part of the problem, and we simply multiply that by the voltage across the plates, which is 6 volts. And we arrive at a stored charge, rounded to 3 significant digits, of 2.66 times 10 to the negative 10 coulombs. Now we could also express this in a more appropriate unit and call it 0.266 nanocoulombs. And we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Gauss Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Gauss Lab, and best of luck on your math and physics journey.